Hello everybody, this is Mr. Arocena, and on today's lesson we are going to be talking about energy distributions and activation energy. But first, let's do a quick startup activity to remind us of what this diagram means. So, in this diagram we have our reactant energies here, and we have our product energies here, and based on what's been drawn, decide whether this is an exothermic or an endothermic reaction. Okay, we'll let you know at the end of the lesson if you're not quite sure. Alright, so we talked last lesson about the reaction energy diagrams, and today we're going to expand that a little bit to explain a little bit more about how to get reactions to actually occur. Now, at room temperature, you may be surprised to know that at room temperature, molecule collisions and atom collisions occur at a rate of about 10 billion collisions per second. That's a lot of collisions, and it's strange because, well, I guess it's kind of strange when we mention that chemical reactions occur because molecules and atoms collide. Now they're colliding at 10 billion collisions per second at room temperature. Why aren't there more spontaneous chemical reactions? Reactions do occur at room temperature, but they tend to be very, very slow, or meaning that when a reaction at room temperature does occur, it doesn't happen with that much frequency. So even though 10 billion things collide per second, maybe only if 1% of them actually undergo some kind of chemical reaction. Okay. Why is that? It doesn't quite make sense given the context that if all particles have to do is collide, then they should be reacting a bunch, but they don't. And that's partly because these 10 billion collisions, not all of them have the right amount of energy. This diagram I'm going to show you is what's called a distribution diagram. It's a particle distribution diagram. I'll write that here, particle distribution diagram. For any of you guys planning on going into some kind of mathematical field, you will probably see a distribution diagram like this in a lot of places, ranging from... Anyways, what this basically means is that this line here tells me kind of the distribution of particles and how many of them are in each segment. So this segment here, so this chunk here, this chunk is the chunk of particles that has a kinetic energy that's here or lower. Okay. So in a sense, if I take this here, all of these particles in this chunk have a kinetic energy that is here or lower. Okay. Now what's neat about this is that this chunk are the particles without enough energy. Particles without enough energy to cause a reaction. Okay. Whereas these particles here, these will be particles with enough energy. Particles with enough energy. So the particles on the left side of this line here have not enough energy, so they don't have enough energy to react. Whereas the particles on this side of the line have enough energy to react. What then is this line? Well, that line is the minimum energy for reaction. Okay. If the particles colliding, we have this minimum energy, so this minimum energy here, then they can react. And as you can see in this particle distribution diagram, not very many molecules will actually have the sufficient energy to undergo the reaction. Okay. And most distribution diagrams will look like this. The only difference is where the minimum energy line happens to be. If a reaction occurs very, very quickly or occurs spontaneously, then the minimum energy line tends to be a little towards this way. If the reaction occurs very slowly or not spontaneous at all, the minimum energy requirement tends to be right. Okay. Now, what then is this T2? Well, T2 represents what happens when you increase the kinetic energy. So basically, what T2 represents, so this T2, let's erase a couple of things. T2 or T2, so this line here represents what happens when you increase the temperature. So when you increase the temperature, you shift the entire distribution to the right because more particles have more minimum energy. So then the particles without enough energy, they still are still represented by this chunk here. But then the particles with enough energy, there's now more of them. Okay. And you kind of noticed this with your lab the other day in that if I raise the temperature, more particles are able to react. Okay. And you even should have noticed that the raise in temperature doesn't correspond to a linear increase, meaning that if I double the temperature, I don't double the amount of reaction that takes place. And that's kind of true in general experimentation. Like here, generally speaking, every 10-degree rise in temperature will double the reaction rate. So if you raise your temperature by 20 degrees, your reaction rate will quadruple. 30 degrees, it will multiply by so on. I think your reaction experiment the other day kind of illustrates that, where it increase the reaction, or we increase the temperature by significant amounts, and therefore the reaction rate also increased by a significant amount. Now this minimum energy, we can actually call this minimum energy, we call this the activation energy, because the activation energy or the minimum energy represents a barrier of energy that needs to be overcome in order for the reaction to take place. Okay. So to represent this on a graph, we're going to expand the energy reaction diagram to look like this. Okay. The reactant energy will still be here. So the reactant energy is always on the left side here. That's my reactants. The product energy will be on the left side. Did I say right then left? Whatever. So reactant energy on the left, product energy on the right. At the top here, it's kind of neat because this is where the activation energy, or activation energy, is the highest, and if the molecules have enough energy to get here, they will form what's known as an activated complex, and we'll talk about that shortly. Delta H, however, is still measured as a difference between the reactant energy and the product energy. It's not, delta H is not, oops. Delta H is not from the, whoops, I told you. This should be products. Okay, so delta H is not measured from the top of the activation energy to the bottom of the products. It's always measured from the difference from the reactant and product energy. Even though you have this huge activation energy here, that's not part of delta H. Okay, that is actually the activation energy. So that's this here. So the difference between the reactant and the top of the activation energy, that is the activation energy. So the activation energy is what the reactants need to gain in order to go down the other side to become products. Okay. And then delta H again is just difference between reactants and products. Some reactions will actually have very low delta H, but could have very high activation energies. Other reactions will have very low activation energies and really large delta H's or whatever. Activation energies are another requirement to overcome. That's the energy requirement in order to overcome, in order to start a chemical reaction. Now, the activated complex is really interesting because at the activated complex, this is what's considered an intermediate molecule, and all the atoms at this point, all the atoms taking part in the reaction just kind of combine, join together momentarily as the bonds rearrange themselves. So as an example, if I take the formation of water, so here's hydrogen. Formation of water requires 2 hydrogens and 1 oxygen molecule. They will collide together in order to create 2 water molecules, like so. Okay. So the activated complex, when these collide, they will actually look like this. So all the hydrogens will then collide with the hydrogens, and somewhere in there are the 2 oxygens. Something like this. And then these bonds will get broken and remade. Okay. So this complex here, this is the activated complex of hydrogen colliding with another hydrogen, colliding with an oxygen, and all the bonds will rearrange at this point, and then they will give you the 2 waters. Now, forming this activated complex does require all of your reactant molecules to sort of collide with each other, and some reactions that's really, really difficult, especially any reaction that requires huge numbers of molecules to collide. One of your assignment questions asked you about octane, the combustion of octane. The combustion of octane was included in one of your assignment questions, asking you which of these reactions occurs slowest. Well, the octane reaction is listed the slowest because, if I'm not mistaken, octane requires something like 25 oxygen molecules in order to combust. And if you can imagine, look like it's basically 25 oxygen molecules all crashing into the octane molecule 25 times all at once, and that's going to be really difficult. And then all 25 oxygen molecules need to have sufficient energy to overcome whatever the activation energy is in order for octane to combust. Okay. This is going to be quite difficult. And given in the distribution diagram we just saw, the chances of all 25 oxygen molecules having sufficient energy to overcome the activation energy will be very small. This is part of the reason why octane doesn't spontaneously combust often at room temperature. Okay, we can get it to combust, we just have to change the conditions slightly to make it more favorable that these oxygen molecules have enough energy, or the octane molecule has enough energy to collide properly. Speaking of colliding properly, one of the things we can do to help alleviate the activation energy is to actually ensure that the molecules collide with each other properly. Okay, now you might be thinking, like, why is that important? Aren't all molecules kind of just arranged as little floating balls in space? It's like, why should the orientation matter? Well, a lot of times we often forget in chemistry that atoms and molecules are actually surrounded in a giant cloud of electrons. So every molecule, like let's say a hydrogen atom, has this cloud, this electron cloud. In the case of hydrogen, it's a single electron just floating around randomly. And then if I want to combine it with, let's say, chlorine, like here, chlorine has also a giant cloud of electrons, but chlorine will have, I think, 30 something electrons. 30. Yeah, I want to say no, wait, chlorine has not 30, sorry, 18 electrons, I think. Yeah, chlorine has 17 electrons. So these 17 electrons, as this hydrogen tries to combine with the chlorine, these 17 electrons are going to do their darndest to repel the lone electron in hydrogen. So trying to get these two to combine can be quite difficult in this case, if they're oriented improperly. Okay. there are some arrangements of between molecules that will actually lessen this electrical repulsion. Take, for example, with water. If you remember from Chem 11, water is a polar molecule, so the hydrogens actually have a slight positive charge, and the oxygen has a slight negative charge. So if I want to combine this to anything, I'd have to arrange it in such a way that the positive end of water is pointing towards the negative end of whatever else we're reacting, so that we can reduce the amount of electric repulsion. Anything we can do to reduce electric repulsion will make the attraction, or it'll make the creation of the activated complex easier, because we can reduce the activation energy. Okay. If things are oriented improperly, the activation energy can get quite large and can prevent your reaction from occurring. All right. So to recap, in order for things to collide, two things need to occur. One, the reactants need sufficient kinetic energy. Okay. And this is so that they can so that they have enough energy to basically overcome the activation energy. So in my reaction energy diagram, I need to overcome this hump in order to actually react. Sorry. Okay. Now, to help us along, proper orientation of the molecules can help reduce the activation energy. So if my molecules are arranged properly, I can reduce the electrical repulsion, and that's key. Reduce the electrical repulsion, and by reducing the electrical repulsion, I can reduce the amount of activation energy needed to cause the reaction. Okay. By contrast, if I want to prevent a reaction from happening, I can force the molecules to meet an incorrect fashion, or sorry, a fashion that promotes electrical repulsion. There we go. Right. If you guys have any questions, you know where to find me. And for now, here. Oh yeah, I just also said I think we're getting close to the end of the unit, so you can probably expect a test at some point early next week. Alright, so yeah, if you guys have any more questions, you know where to find me. And for now, here is your next assignment.